Hello, good evening, friends. I am Tarush Mehta. I am currently doing MTech in electrical engineering in the specialization RF and Photonics, EE5. So today I am going to present a presentation on the introduction to photonics. So let me share my screen. So introduction to photonics. Firstly, what is photonics? So photonics basically refers to that branch of technology that deals with the properties and transmission of photons. So in short, it is the study of light. Photonics is divided into four parts. The first is the ray optics, the second is the wave optics, the third is the electromagnetic optics, and the fourth is the quantum optics. Now let's study each of these theory one by one. So we start with the ray optics. In ray optics, light is assumed to travel in straight lines, and it is governed by some geometrical rules or laws. So this theory was first proposed by two scientists, Newton and Fermat. Now ray optics is a valid theory whenever the dimension of the object is much larger than the wavelength of the light that is being used. So in ray optics, the light has to obey some rules which are geometrical in nature. So two of such rules are the laws of reflection and the laws of refraction. So first, let us see the laws of reflection. So there are two laws of reflection. The first is as we can see in this figure, that the incident ray, the reflected ray, and the normal, which is drawn at the point of incidence, all the three lie in the same plane. And also, the angle of incidence is equal to the angle of reflection. And both these angles are measured with respect to this normal. Now, coming to the laws of refraction, refraction also means transmission to some another media. So, whenever light is traveling from one media and it enters into another media, then the light is observed to bend either towards the normal or away from the normal, depending upon the ratio of the refractive indices of the two media. And the angle of incidence and the angle of transmission, theta 1 and theta 2, are related by a famous law called as Snell's law, which is given by n1 sine theta 1 is equal to n2 sine theta 2, where n1 and n2 are the refractive indices of medium 1 and 2 respectively. Now, using these two laws of reflection and refraction, we can explain the working of various optical components like lens and mirrors. For example, we can see on the figure on the left, here a convex lens is shown where the light rays emerging from far away from the lens, whenever they strike the lens, they converge towards a point called the principal focus. Similarly, as we can see for this concave mirror, that the light rays emanating from some point in infinity, whenever they strike the mirror, they converge towards a fixed point called the principal focus. And the image formation through these various types of mirrors and lenses can be explained using the principles of ray optics. For example, in a convex lens, the image formed is real and inverted, whereas in a concave lens, the image formed is virtual and erect. Then, depending upon the position of the object, the size of the image as well as the distance of the image from the mirror or the lens also changes. And all these phenomena can be explained using ray optics. Another optical component that can be explained using the theory of ray optics is the optical fiber. So going back to the Snell's law, here we can see that whenever light was incident from a medium that had a lower refractive index to a medium that had higher refractive index, light bended towards the normal. Now, if the reverse thing happens, suppose if the light is incident from the water into the air, so water has higher refractive index and air has lower refractive index. So water is called denser medium and air is called rarer medium. So whenever light strikes, light enters from water to air, the light ray is observed to bend away from the normal, just opposite to what happens when it enters from air to water. So it is possible that whenever the light is entering from a denser to a rarer medium, up to a certain angle, the light will transmit to the other medium. Beyond a certain angle, the light will simply graze at the boundary of the surface, in which case the transmission angle will become completely 90 degrees. So if theta 2 is the incident angle and theta 1 is the transmission angle, then theta 1 will completely become 90 degrees. Whenever the light is incident beyond that value of angle, then the light will no longer get transmitted or refracted, but rather it will get reflected or bounced back within the same medium. So this phenomenon is called the total internal reflection. And this occurs for the incident angles beyond a certain angle. And that angle is called the critical angle. So now coming to this optical fiber is basically made up of two elements. The center element through which the light propagates is called the core of the optical fiber, and the outer element is made up of a refractive index lesser than that of the core, and that is called the cladding. So generally, both core and cladding are made up of SiO2, but in core some impurities are also there. So as we can see, whenever the light is incident at the core of the optical fiber, it goes and strikes the core cladding interface. Now at the core cladding interface, the light experiences total internal reflection, and so it bounces back. And similarly, it makes multiple reflections at various points on the core cladding interface, and in this way the light propagates through the optical fiber with minimum attenuation. But in order for the total internal reflection to happen, or for the light to propagate through the core, the incident angle at this core cladding interface must be greater than the critical angle. And for that to happen, the incident angle at the air core interface for the light must be lesser than the acceptance angle. So this can be proved using the laws of reflection and refraction. And we will find out that the acceptance angle for an optical fiber is given by sine inverse of numerical aperture, where numerical aperture is nothing but under root of n1 square minus n2 square, where n1 is the refractive index of core and n2 is the refractive index of cladding. So only the light rays that are striking the optical fiber with angles lesser than this acceptance angle, those light waves can only be supported through the optical fiber and can propagate through the optical fiber through total internal reflection. Now, another set of materials or optical components that can be explained using the principles of ray optics are the optical waveguides. So, in order to define an optical waveguide, we look at this definition: a medium of refractive index n1, which is embedded in another medium of lower refractive index n2, can act as a light trap within which the optical rays remain confined by multiple total internal reflections at the boundaries. So basically, the optical fiber that we were looking was also a special case of this optical waveguide. So in optical waveguide, the light remains confined within some boundaries and within a structure. So for example, here we can see various examples of optical waveguides like straight waveguide, S-bend, then Y-branch. So this Y-branch waveguide is used if we want to split the input power into two halves or in two ratios at the two output ports, then we make use of this Y branch. Then Mach Zehnder interferometer is used if we want to split the light into two parts, and one of the part should give some phase difference with respect to the other, and then we want to interfere them, then this Mach Zehnder is used. Then if we want to couple some small amount of light from one fiber to the other fiber, then we make use of directional coupler. So these are few examples of optical waveguides, the basic working of which can be again explained using ray optics. Now coming to the second theory of light or theory of the photonics, this is wave optics. In wave optics, light is considered. So basically in ray optics was good to explain many phenomena like the image formation through lenses, mirrors, and which are two most common devices that we observe in our day-to-day surroundings. However, ray optics fails to explain the phenomena like diffraction and interference. So in order to explain such phenomenon, wave optics was introduced. So in wave optics, light is considered to propagate in the form of waves. And this theory was first proposed by Christian Huygens. So as we can see here, every wave has a wavelength and a phase associated with it. So wavelength is basically, so here light is considered to be traveling in the form of some wave, and this wave is scalar in nature. And the distance between the any two consecutive maxima or any two consecutive minima is called a wavelength. So here light is no longer to be assumed to travel in straight lines as it was in the case of ray optics. And phase basically refers to the start point of this wave. So how much it has been delayed with time as well as position from the starting point. Now, in order to find different solutions or different possible waves in which the light can propagate, we make use of the Helmholtz equation, or which is also called the waves equation. So this is basically a partially differential equation where u is the solution of that, and u represents the scalar wave. So Laplacian square u minus 1 by c square del square u by del t square is equal to 0. And c is the speed of light. And the speed of light is observed to decrease or is observed to change in different media having different refractive indices. For example, the speed of light in vacuum or air is approximately c0, which is 3 into 10 power 8 meter per second. But in a medium with refractive index n, the speed of light becomes c0 by n. And the wavelength is basically given by the speed of light divided by the frequency, which is denoted by nu. So again, the basic phenomena like reflection as well as refraction, both could be explained using wave optics also, as it was done using ray optics. So as we can see, the light wave striking here, the light wave that is striking the surface gets reflected back. And again, the same laws of reflection and refraction can be used here. For example, angle of incidence will be equal to angle of reflection. As we can see in this second diagram, the light wave incident is getting transmitted, and light wave incident from air is getting transmitted in water. And apart, so the laws of reflection and laws of refraction are obeyed here, which is the Snell's law. So the theta 2 is lesser than theta 1 because this light ray is bending towards the normal. Also, the speed of the light in water is lesser than the speed of the light in air. And we can also see the wavelength of the light in water is lesser than the wavelength of the light in air. However, the frequency of the light remains constant when light propagates from one media to other media. So this is the relation that both the speed of light as well as the wavelength gets reduced by a factor of n with respect to air if the where n is the refractive index of that particular medium. However, the wave number k increases by n times. Now moving on to a very important phenomenon called diffraction. So this diffraction could not be explained using the principles of ray optics. So basically, diffraction refers to the bending of light whenever light is transmitted through an aperture whose size is comparable to the wavelength of light. For example, as the aperture size here is reduced, the incident light that is striking this aperture is observed to bend at the output side. And if we place a screen at the output, we can observe different maximas and minimas, which are formed due to either constructive interference or destructive interference, respectively. So we can also find the position of nth order maxima with respect to the center using the formula d sine theta is equal to n lambda, where d is the slit width, theta is the position of this maxima. If we draw a line like this, then this angle, if we draw a line to the maxima, then the angle that line will make with the horizontal is basically theta, and that angle starts from this center of the slit. And n is the number which is corresponding to nth order maxima, and lambda is the wavelength. So d sine theta is equal to n lambda. And also sine theta can be approximated to tan theta, which is nothing but y by d, where y is the position of the nth order maxima from the center of the slit, and capital D is the distance of the screen placed from the slit. So using that equation, we can find that which maxima is positioned at which location with respect to the center of the slit. One of the important optical component, that is diffraction grating, works on this principle of diffraction. So diffraction grating is basically an optical component that is used to periodically modulate the amplitude or the phase of an incident wave. For example, if a white light is incident on a diffraction grating, we can see that white light is made up of 7 colors, and each of these 7 colors have different wavelengths, and so they get splitted out by this diffraction grating. And we can see all these 7 colors here. The next phenomenon, which could not be explained by the ray optics, but could be explained using the wave optics, is the interference. So interference basically refers to the mixing of 2 or more waves in simple language. So whenever 2 or more waves are simultaneously present in the same region of space and time, the total wave function is the sum of individual wave functions. So here we can see that there are 2 waves and with some phase difference between them. So whenever these 2 waves are added, wherever the phase, then the resultant wave that is obtained is shown here in pink color. Now, whenever the phase difference between these 2 initial waves was 0 degree or some even multiple of 2m pi or even multiple of pi, then the intensity of this resultant wave goes to maximum. And whenever the phase difference is some odd multiple of pi between these 2 initial waves, then the intensity of the resultant wave becomes 0. So wherever the intensity of the resultant wave becomes maximum, that thing is called the constructive interference. And whenever the intensity of the resultant wave becomes minimum, then it is called destructive interference. So constructive interference happens whenever the phase difference is some even multiple of pi, and destructive interference happens whenever the phase difference between the 2 combining waves is equal to some odd multiple of pi. So the combined intensity in general for some angle phi can be written as I is equal to I1 plus I2 plus 2 root I1 I2 cos phi, where phi is nothing but the phase difference of the wave 2 minus the phase difference of wave 1. Now the same thing could be observed using the slit experiment also, if we just have two slits instead of one single slit. So when the light wave is entering, because of the phenomenon of diffraction, it gets bended at each of the slits. Now the light bending at each of the slits can be regarded as one wave. So there are two waves that are generated in the space right to the slit, and both of these waves interfere and they give an interference pattern, something as shown here. So again, we can see some bright spots which are the maxima and black spots which are the minima. And this is happening because of interference. Now, based on this particular theory of interference, a very important class of devices called the interferometers are developed. And these interferometers can be of three types: Michelson interferometer, Mach-Zehnder interferometer, and Sagnac interferometer. So Michelson interferometer is used to measure the distance or the displacement of some particular mirror. So let's see how does a Michelson interferometer work. So as we can see here, a Michelson interferometer consists of a light source which emits a light of intensity U0, and this light of intensity strikes a beam splitter. Now the work of the beam splitter is to split this input intensity or input light into two different lights having different intensities U1 and U2. Now the light waves having the intensity U1 strikes the mirror 1 and it gets reflected back towards the beam splitter, and the same thing happens for the light ray having the intensity U2, it strikes the mirror 2 and gets reflected back towards the beam splitter. Now both of these light waves are combined at the beam splitter and they move towards the photodetector. So at the photodetector, we get the intensity U of R again as U1R plus U2R. Now, if both these mirrors M1 and M2 are placed at equal distances from the beam splitter, then the phase difference between U1 and U2 would be 0, which would lead to a constructive interference and the intensity would become maximum. Now, whenever the mirror M1 is moved by some distance, then there will be some phase difference introduced between M1 and M2, and so the intensity starts decreasing from the maximum value 4I0. And if this phase difference becomes exactly equal to pi or any odd multiple of pi, then then a destructive interference happens and the intensity becomes 0. So we get the graph of intensity versus the moved distance of the mirror M1D as shown here. So the intensity oscillates between maximum and minimum value. Now by measuring the intensity at any point of D, we can basically measure how much phase change has taken place, and by measuring that phase change, we can also measure the displacement D of the mirror from its initial position. So this is all we need to know about Michelson interferometer. Moving on to the next interferometer, it is Mach-Zehnder interferometer. So Mach-Zehnder interferometer is used for measuring the refractive index of some material. So we can see that the structure of the Mach-Zehnder interferometer looks something like this. So again, we have a laser source, and this time we have two beam splitters. So the light wave that falls on this beam splitter again gets splitted into two intensities, U1 and U2, and both of these intensities again recombined at the screen through the beam splitter, through the second beam splitter. Now the distances of this distance plus this one is actually made equal to this plus this, so that the path length for both the uh, light waves remain the same and no phase change occurs normally. However, when in the second or in this particular arm, if we introduce a material of some unknown refractive index, then these two waves that are striking the second beam splitter will not be in phase, and that phase delay will be caused because of this because of this material, as the light wave will slow down inside this material. So both of these light waves will reach at different time, leading to some phase difference between them. And because of that phase difference, again we will see an intensity pattern versus D, something like this. So whenever we measure measure the intensity at the output, by measuring the intensity at the output, we can say that how much phase difference or phase change has taken place. And by measuring that phase change, we can find out the refractive index of this particular material. And these Mach-Zehnder interferometers are also used for the design of optical switches and sensors. The third type of interferometer is the Sagnac interferometer. So the basic structure of a Sagnac interferometer is shown here. So in Sagnac interferometer, basically three beam splitters are used, and here the light coming from the laser or any other light source, when it strikes the first beam splitter, actually totally a total of four beam splitters are used, and when the light strikes the first beam splitter, the light one part of the light wave travels completely clockwise, and it reaches again the first beam splitter and then goes to the detector, whereas the second light wave which got splitted here just travels counterclockwise, coming through all of these beam splitters and finally falls on this detector. Now, if this setup is at rest, then both of these light waves that will recombine at the detector will have the same phase, and so always constructive interference will take place. However, if the setup is moved with some angular velocity in clockwise direction, then one of the light wave, either the then one of the light wave, that is the clockwise moving light wave, will get slowed down as compared to the counterclockwise wave. And because of this, both will arrive at the detector, both the clockwise and the counterclockwise wave will arrive at the detector, but not at the same time. There will be some delay between their arrival. And because of the delay, again, a phase difference between the clockwise and the counterclockwise wave would be created. And so, by measuring the intensity at the output, we can measure that how much phase difference or phase change has taken place. And by measuring that phase change, we can measure with what angular velocity this setup was moving, in which direction, and also in which direction it was moving. For example, here we can see that the delta phase change is given by 8 pi times numerical aperture by lambda c times the omega, where capital omega is the angular velocity. So this concept of measuring the angular velocity can be exploited, and so Sagnac interferometers can be used for the design of optical gyroscopes, which are in some form much more accurate than the old mechanical gyroscopes. So this completes the wave optics, and now we move on to the third theory of light, that is electromagnetic optics. So according to this theory, light is an electromagnetic wave which has two mutually coupled vector waves, electric field and magnetic field, both of which are time varying in nature. So in wave optics, we were treating the light to be as a scalar wave, but in electromagnetic wave optics, light is assumed to be a vector wave, which itself comprises of two vector components, electric field and magnetic field. So we can see that the electric field oscillates in one direction, and the magnetic field oscillates between a maximum and minimum value in the transverse direction to that of the electric field, in such a way that both this electric field and magnetic field are perpendicular to each other, and the electromagnetic wave propagates perpendicular to both this electric field and magnetic field. So this is the basic structure of an electromagnetic wave. Now moving on to the electromagnetic spectrum. So based upon the different frequencies or the wavelengths, different frequency ranges and different wavelength ranges in this electromagnetic spectrum are given different names. For example, for very short wavelengths, we have gamma rays and X rays. Then UV rays or ultraviolet rays correspond to a wavelength range of about 10 nanometers to 330 nanometers. And these UV rays are generally used for various absorption spectroscopy experiments. Then the visible between this UV rays and infrared, we have the visible light, and this visible light is the one white light which comprises of the 7 colors Vibgyor, and this is the visible part of the electromagnetic spectrum to our human eyes, and also this part is used for basically all our lab experiments. Then moving further, we have infrared rays, in which so the wavelength range for this visible light is from 330 to some 760 nanometer, and then we have the infrared rays or IR rays, which have a wavelength ranging from some 760 nanometers to up to 300 micrometers. So these infrared rays are basically the near infrared rays are used for telecommunication in optical fibers, and the far infrared rays or the middle infrared rays are used for the identification of various kind of biomolecules. Moving further, we have the microwaves and the radio waves. So generally, the optical spectrum corresponds to the ultraviolet, visible, and the infrared region of the electromagnetic spectrum. So basically, these three regions of the electromagnetic spectrum are termed as optical spectrum. Then the relationship between the electric field and the magnetic field, or the solutions of the electric field and the magnetic field for any electromagnetic wave, is obtained through the 4 Maxwell equations. So these are Gauss law, which basically says that the divergence of the displacement vector D is equal to the charge density enclosed within a surface. So this is the differential form of Gauss law, and this is the integral form of Gauss law. So here we can say that the integral of this d dot ds, or the flux, the net electric flux that is coming out of a surface, is equal to the charge enclosed. Then we also have a Gauss law in terms of magnetic field, which is simply stated as the divergence of the magnetic field vector is equal to 0, or the net magnetic flux coming out through a closed surface is always equal to 0, which also means that that magnetic monopoles do not exist. So magnetic poles always exist in pairs, that is North Pole and South Pole. So how much ever we cut a magnet, always the magnetic poles will exist in pairs, North Pole and a South Pole. Then the third law is the Faraday's law, which states that curl of electric field is equal to minus del B bar by del T. Or in integral form, integral E dot dl over a closed curve C is equal to minus del B by del T times ds. So this basically states that the EMF induced across any closed curve is equal to the rate of change of flux through the area enclosed by that curve. And based on this Faraday's law, most of the motors, generators, and transformers work. The fourth is the Ampere's law. So Ampere's law states that curl of H bar is equal to J plus del D by del T. So this del D by del T is also called the displacement current, and J is displacement current density, and this J is called the conduction current density. So basically, the or in integral form, integral H dot dl becomes J plus del D by del T dot ds. So basically, if we perform the integration of magnetic field vector with the length vector across any closed curve, that integration will be basically equal to the total current coming out from that surface, because integral J dot ds represents the current. So integral of H dot dl is equal to the current enclosed by that surface. Now by solving these Maxwell equations, we can get various types of wave solutions. So here are listed some elementary electromagnetic waves. Like we can see on the extreme left that this is a plane wave, then this is a spherical wave. So and this is an example of a Gaussian wave, where in Gaussian wave the intensity is maximum at the center and it decreases towards the outer edges. Whereas spherical wave again is described by a e power minus jkr by r, and a plane wave is just described by a e power minus jkr. So any other wave solution that is obtained from the Maxwell equations can be written as the superposition of one or more elementary waves that are shown above. Now seeing the behavior of these electromagnetic waves. So again, if we try to write these Maxwell equations in source-free region where there is no sources, then we'll get this J is equal to 0, and also this rho v is equal to 0. And then by solving these four Maxwell equations, we will get an equation similar to that of the Helmholtz equation, but this U will be replaced by the electric field and magnetic field. So basically, we will have del square E bar minus 1 by C square del square E bar by del T square is equal to 0, and del square H bar minus 1 by C square del square H bar by del T square is equal to 0. So just the U will be replaced by E or H. And basically, those two equations again describe the propagation of the electromagnetic wave through some medium. Now, if we want to observe the properties of these electromagnetic waves in dielectric media, then we define a vector called the polarization vector, which is given as the epsilon naught times the susceptibility times the electric field, where this xi is the susceptibility of the medium. And the displacement vector and the B vector are related with the electric fields and polarization vector, also given by this equation. So again, these are some equations through which we can also define the refractive index of a material, that is given by root over 1 plus xi, where xi is the susceptibility. Now coming to a very important phenomenon called the polarization of light, which was actually not present in wave optics. So wave optics could explain most of the phenomena like diffraction, interference, and also the basic phenomena like reflection, refraction, but it failed to explain the working of the beam splitters and all, which involved the concept of polarization. So polarization basically refers to the movement of the electric field vector at a fixed point in space with respect to time. So since an electromagnetic wave consists of electric field vectors and magnetic field vectors, both of which are mutually perpendicular to each other and also perpendicular to the direction of the wave. So whenever a wave is propagating, it is interesting to know how does the electric field pattern changes with respect to time, or how the electric field evolves with respect to time. So there are basically two types of polarization. One is linear polarization, the other one is circular polarization, and there can be, of course, also be elliptical polarization. So the wave is said to be linearly polarized whenever the phase difference between the x and the y components of the electric field is 0 or 180 degrees. And the wave is said to be circularly polarized whenever the phase difference between the x and the y components of the electric field is 90 degrees or pi by 2. and the amplitudes of the fields along x and y directions are equal. Now, if the phase difference between the x and y component is any other value, and also the amplitudes in x and y directions are not equal, then the wave is said to be elliptically polarized. Now here we can see, as the wave is propagating, the electric field vector is moving or evolving in a circular fashion. So this is an example of circularly polarized or circularly polarized light. And here we can see that as the light is propagating, after crossing this quarter wave plate or some material, the variations of the electric field is having oscillations along one plane, in the linear direction along one plane. And so this is an example of linear polarization, or it is sometimes also called planar polarization. And these quarter wave plate or linear polarizer are basically the materials that help to change the polarization of light. For example, this quarter wave plate was converting the circular polarization to a linear polarization. Now moving on to the again basic phenomena like reflection and refraction. So this could be explained using electromagnetic optics also. So here again, let us consider two different materials. One is having refractive index N1, the other one is having refractive index N2. So the incident wave is getting reflected here, and also a portion of it is getting transmitted. So again, the same laws of reflection, that is angle of incidence equal to angle of reflection, and the Snell's law for the law of reflection can be proved here with respect to electromagnetic optics also, as it was done in the case of ray optics and wave optics. The additional things that come into play here are two types of are basically how much amplitude of the electric field that is incident is getting transmitted and also reflected. So that is basically given with the help of Fresnel equations, which can be derived using the Maxwell equations along with the boundary conditions. And these are something like this. So using these equations, we can find that how much part of the electric field is transmitted to the new medium and how much part of the electric field is reflected back. And with this, we can also get an estimate of how much power is transmitted to the second medium and how much power is being reflected back to the first medium. Then coming to an important optical component called wave retarder. So basically, a wave retarder is some kind of optical component that can convert the state of polarization of light. For example, a quarter wave retarder can convert a linear polarized light into a circularly polarized light, or a circularly polarized light into a linearly polarized light. And a half wave retarder can rotate a linear polarized wave by some angle, as it can be seen here. And it generally rotates by 180 degrees. Similarly, if it is a circularly polarized light, it changes the state of polarization, because a circularly polarized light can be either right-hand circularly polarized or left-hand circularly polarized. So this half-wave retarder converts a right-hand circularly polarized light into a left-hand circularly polarized light, or vice versa. So with this, we finish the electromagnetic optics. And now we move on to a very important theory, which is being used the most, and it is the quantum optics. So with electromagnetic optics, most of the phenomena could be explained, but they were valid in the classical regime. So now, to go into the quantum regime, we make use of the quantum optics. So here, light is, according to quantum optics, light is assumed to be made of discrete particles or packets of energy called photons. And also the absorption and emission of light is quantized. That is, absorption or emission of light happens through discrete levels or discrete packets of energy called photons. And this theory was first proposed by Albert Einstein and Max Planck. The theory of electromagnetic optics was first proposed by James Clerk Maxwell. So in order to understand the quantum optics or how do photons interact with matter, we need to study three basic quantum mechanical phenomena, which are absorption, spontaneous emission, and stimulated emission. So first is the absorption. So whenever an incident photon, so according to quantum optics, every material was assumed to have some discrete energy levels as shown here. And also the emission of and transmission of light was quantized. That is, light consists of particles called photons, which are discrete in nature. So whenever the incident photon energy, now usually the electron will reside in the lower levels. So whenever an incident photon energy matches the band gap of the material, this photon is absorbed by that material, and using the energy of this photon, an electron gets excited. This electron, which was in the lower state, gets excited to the higher state. So this is basically called absorption. Now the lifetime of an electron in a higher state is very less, and so it immediately falls back or decays to the lower state. And because of this decaying, spontaneously a photon is emitted. So this is basically called spontaneous emission. Now, if an electron in an atom is in the upper energy level and the radiation mode also contains a photon, and if this incident photon is triggering the emission of this particular electron, then there will be two photons coming out, one due to the emission and one is this photon that just passes away. And this is basically called stimulated emission. And here, both the photons that come out will be identical in all aspects, like they will have same momentum, same energy, same phase, same amplitude, etc. So whenever the emission happens because of the triggering by some incident photon, it is basically called stimulated emission. Now, having the knowledge of these three basic phenomena, absorption, spontaneous emission, and stimulated emission, it becomes easy for us to describe any quantum phenomena. For example, one such phenomena is the absorption spectroscopy. So basically, this method makes use of the wavelength-dependent absorption characteristics to identify different materials or substances. So different materials have different band gaps, and so they absorb photons of different energies. So by seeing their absorption spectra, we can identify that we can identify or distinguish between different materials. Now, whenever the light source is passed through some medium that has some fixed concentration, then the absorption through that medium is given by the Beer's law, which is absorption equal to epsilon times BC, where B is the length of the cuvette, C is the concentration of the substance that is placed inside that medium. So if the concentration of this medium is more, then more light will be absorbed through this medium. Also, if the length of this cuvette is more, the absorption will increase. Next, coming to the fluorescence mechanism. So fluorescence refers to the phenomena by which a material absorbs light of a particular wavelength and emits out light of another wavelength. So the concept of fluorescence can be basically explained by whenever an incident photon is there, it will excite an electron from the lower ground state to some higher state, higher energy state. Now here the electron is momentarily unstable, and so it will decay in a non-radiative fashion, and it will come down to the state 0. Now this electron in the state, and this energy will be given in the form of heat. Now the electron in the state 0 this state 0 will again decay back or again come back to the ground state, because of which light because of which a photon of different wavelength will be emitted. So the absorption the photon which was used for the absorption had a wavelength of the energy difference between this E3 minus this E0, whereas the emitted photon has a wavelength of this E0 minus the E0 of the ground state. So as we can see, the two photons have different wavelengths. So in by this process, the material, we can see that the material is absorbing light of a particular wavelength and emitting out of light of another wavelength. Also, many materials like naturally occurring materials like chlorophylls and all use the properties of this or show the property of this fluorescence. Now we try to move to the design of different kind of optical materials, which can be either optical sources or optical detectors. So for their design, we generally make use of semiconductors. Now, semiconductors can be of two types. So as we know, every semiconductor has a conduction band and a valence band. The valence band is the one in which the electrons reside at room temperature. And upon excitation, these electrons move to the conduction band. So if we draw the energy momentum diagram in any semiconductor, it can be basically of two types. One is this one in which the conduction band lower edge and the valence band upper edge will coincide, which is also called a direct band gap semiconductor. And the other one is in which this conduction band edge and the valence band edge will be shifted with respect to each other, and this is called the indirect band gap semiconductor. So in a direct band gap semiconductor, whenever an electron falls from the conduction band to the valence band, a photon is emitted out. This happens because the momentum change is nearly zero, and that zero momentum change can be given to a photon because photon also has negligible momentum because of having negligible mass. So both energy and momentum conservation are taking place here. Similarly, in an indirect band gap semiconductor, whenever an electron falls from a conduction band to a valence band, there is some momentum change. So that momentum cannot be retained by a photon. So along with photon emission, we also have phonon emission, and actually phonon emission is more dominant in indirect band gap than photon emission. And so whenever we try to design any device that can emit out light, we make use of this direct band gap semiconductor, because in direct band gap only, after the recombination of this electron and hole pair, a photon can get emitted out. Now coming to a very important optical device or optical source rather is the laser. So laser stands for light amplification by stimulated emission of radiation. So basically laser works on the principle of stimulated emission, where a external photon triggers the emission of a photon of an electron, or an external photon triggers the emission because of which a new photon is emitted, and these two photons are said to be coherent because they are identical in all respects. Now, if by some mechanism we can pump out, if we can, now these two photons will, if there is another electron at the excited state, then these two photons will again make that third electron also to fall, and in this way some three identical photons will be generated, or three identical photons will be emitted. So like this, because of one stimulated emission taking place, that one stimulated emission can trigger multiple such stimulated emissions, depending on the population of the electrons in the excited state. So we need to have continuously many electrons pumped in the higher state from the ground state. So for this, we use various kind of pumping mechanisms. And also this, if we can have some kind of feedback mechanism, or also if we can have some kind of a cavity that will actually reflect these photons back, so that these photons can again undergo stimulated emission repeated number of times, then the gain will further increase. So basically, light amplification is happening by stimulated emission, and also a pumping mechanism is required, and also a feedback is placed. So the material along the gain material along with the pumping mechanism and feedback is basically called the laser. So here we can see for providing the feedback, these cavities are placed, which will actually reflect the photons back so that it can be further multiplied in such a way that the final output beam that is coming out of this cavity will be of high power, and also it will be monochromatic. That is, it will have only a single wavelength, as a single wavelength is being ejected out, and that single wavelength is being continuously fed back and also amplified. And this is the basic diagram of stimulated emission. Now there can be various mechanisms of pumping the electrons to the excited state, because that is very important for increasing the gain of the laser. So one of the way can be through pumping through some cathode and anode. The other way can be pumping through a flash lamp. And these are again some other examples. So we can have an erbium doped silica fiber also, which can act as a laser. Then moving on to the other optical source, that is LED, light emitting diode. So now basically an LED is also made up of semiconductor and from a simple PN junction diode that is in forward bias condition. So in forward bias condition, recombination takes place in the depletion width. So we can see this is the basic internal structure of an LED, and this is the outer structure that we have installed in our various homes. So the basic working of this LED can be explained as whenever a P-type semiconductor and an N-type semiconductor are brought together, a depletion width is formed in between. Now, this depletion width will be depleted of the carriers, and there will be almost negligible carriers in this depletion width to support any current. However, when this PN junction is basically connected to some kind of battery in forward bias condition, then the P-type semiconductor, which are then the P-type semiconductor, which are actually having holes in minority, which are having electrons in minority, will try to get attracted, and the holes in this P-type will try to get pushed towards the depletion region, and the reverse thing will happen for the electrons. So the electrons which are majority in N-type, they will try to get repelled by this negative charge, and these electrons will move towards the depletion region. And because of this positive charge, the holes which are majority carriers in the P-type will try to move towards the depletion region. So because of this holes, so the depletion region, which was normally devoid or empty of any carriers, will now have both these holes and electrons, will now get various number of holes and electrons because of this battery connected. And because of the recombination of these holes and electrons, light will be emitted out. Again, we need to use a direct band gap semiconductor for the construction of LED or a laser. Now, one of the key difference between the LED and the laser is that in laser starts conducting, or the current starts flowing in a laser only after a fixed value of some threshold current. Means, the laser starts emitting light out only after it is given a fixed amount of threshold current, which may be some close to some 200 milliamperes. However, in an LED, light starts emitting out starting from a small value of current also. And as we increase the current, the output power of the LED increases. And the output power of the laser also increases, but beyond a threshold. Now coming to another important phenomena, which is called the photoelectric effect. So whenever a photon strikes the surface of a material, an electron is ejected out, and this is called photoelectric effect. For example, if we see here, the photons are striking the metal surface, and the energy of the if this energy of the photons is more than the band gap of this metal, or more than the work function of the metal, then electrons are ejected out of this metal. And these electrons may also gain some kinetic energy. Also, in this example, where we have an encapsulated tube or evacuated chamber, here, whenever the radiated and photons are being radiated and they strike the material, an electron is being ejected towards the anode. But the difference between these two structures is that here the emitted electrons are going out of the material, and here the electrons are still remaining confined to this material. So basically, the one shown on the left side is called external photoelectric effect, and the figure shown on the right side depicts internal photoelectric effect. Now, based on this photoelectric effect, we can design photodiode or photodetectors. So in photodetector, just the opposite thing happens as, as compared to what happens in laser or LED. So in laser or LED, we are supplying some current, and output generated is some kind of light wave of a particular wavelength. However, in photodiode, we excite the material with light, and we observe that some current is generated. So we can see that whenever a photon energy illuminating a material is sufficiently large, then it can make the excited electron escape over the potential barrier of the surface of the material. And this is basically working on the phenomenon of photoelectric effect. Now, for the design of a photodetector also, we use a simple PN junction diode. So whenever some photons are incident on this PN junction, then new electron hole pairs are generated. And in order to capture these electron hole pairs or collect these electron hole pairs, so whenever incident photons strike the surface of the photodetector, there are electron hole pairs which are generated, and these generated electron hole pairs need to be collected at the contacts so that they can contribute towards the flow of current. So for that, we again connect the battery, but this time in reverse bias. So the electrons get attracted towards the positive terminal of the battery, and the holes get attracted towards the negative terminal of the battery, thus making the current to flow. Now, the performance of a photodetector is characterized by few metrics like quantum efficiency and responsivity. For example, quantum efficiency is defined as the number of electron hole pairs collected by the total number of incident photons. So it is not like every photon that is incident will give rise to one electron hole pair, and that quantity is basically decided by this quantum efficiency. The responsivity is basically defined as the photocurrent that is being generated divided by the incident power, or it can also be written as quantum efficiency times E by h nu. So we want the responsivity as well as the quantum efficiency of a photodetector to be as high as possible. Then coming to a new class of optical systems or components called the optical modulators. Although the word appears to be new, but we have already seen various optical modulators in the previous slides. So optical modulator is any device that is used to modulate the light or change some properties of the light, like it can either change the wavelength of light, or it can change the position of the light or polarization of light, etc. So these optical modulators are again classified into two types. One is absorptive modulator, working on the phenomenon of absorption, and the other one is refractive modulator. The refractive modulators is further classified into two types: electro-optic modulator and acousto-optic modulator. The electro-optic modulators can either perform phase modulation, amplitude modulation, or polarization change. And the acoustic optic modulators use sound waves for performing the modulation. So here we can see the acousto-optic effect. So sound waves can be used to create a periodic variation in the refractive index of some medium. And because of this periodic variation, whenever the light strikes that medium, that light gets again splitted out because of variation in the refractive index that has been created by sound, because sound is a mechanical wave and it can create some kind of pressure on the medium, because of which the refractive index of the medium can change. So whenever the light is striking, it gets splitted out, and a modulation, because of this modulation of refractive index, the light is splitted out. The second kind of optical modulator is the ones which work in under the electro-optic effect. So whenever electric field is applied to some material, then it can cause a change in refractive index of that material, and because of which the light wave that is incident gets again modulated when it comes out from that material. So this refractive index can either vary linearly with the applied electric field or in a quadratic fashion with the applied electric field. This linear variation of the refractive index with the applied electric field is called the Foucault's effect, and this quadratic variation of this refractive index, or the materials which show this quadratic variation of this refractive index with the applied electric field, that effect is called Kerr effect. Finally, coming to the last topic, which is nonlinear optics. So as we saw earlier, that polarization was equal to epsilon xi times E, but we can have several other processes like second harmonic generation and third harmonic generation. And because of that, the expression for polarization becomes epsilon naught xi1 plus xi2 E square plus xi3 E cube, and so on. So basically, nonlinear optics, in linear optics is also called the optics of weak light, because whatever the absorbed photon is there, the energy of the absorbed photon and the emitted photon or the transmitted photon actually match each other. But in certain processes, we can see that the absorbed photon was of energy omega 1 and the emitted photon has an energy omega 2, because there was absorption taking place 2 times, and the emitted photon was directly coming from the excited state to lower state. So this is an example of nonlinear optics, and this is called second harmonic generation. Even the fluorescence that we observed, where light of a particular wavelength was being absorbed and light of another wavelength was being emitted, that fluorescence is also an example of nonlinear optics. Similarly, we can also see the third harmonic generation example. So here omega 3 coming out would be 3 times omega 1. So the emitted photon does not have the same energy or frequency as the absorbed photons. And other phenomena or examples of nonlinear optics are Raman scattering and Brillouin scattering. Thank you.